So a funny thing, I recorded 2 whole lectures without forgetting to turn my screen on. So this is my second time through doing this. The next thing we're going to do is put everything we've talked about together into one table, this table right here. But before we do that, I want to talk about using different things as units. For example, my truck, Toyota Tundra, weighs anywhere from 5,170 to 5,680 pounds. Let's say 5.4 kips is the weight of a Tundra. Elephants, they weigh anywhere from 6,000 to 13,000 pounds. The one I saw in Kenya when I was there looked just like this one right here. Except the one I saw was crazy. What they did at this safari park was they tied these little packages on the top of heads of elephants that had attacked people and were considered dangerous. And they told me crazy. And the one we saw had one of those, but at the time it wasn't red. It's like a brown little package up there. And at the time, I didn't know what it meant. And later on, I found out it meant that they were dangerous. Anyway, let's say an elephant weighs 13 kips. And we have VC, 2 square root F prime C, B times D. And remember, F prime C here has to be in PSI. And so we had designed a 12 by 24 inch beam. Let's say D is 21.5. And you plug that in, you get 32,600 pounds or 32.6 kips. That's quite a lot. So on that cross section of a 12 by 24, the concrete can hold 32.6 kips. What this means is that 100 kips, you could say that's 18.5 Tundras, 7.7 African bush elephants, or 3.1 VCs. We're going to use VC as a unit of measurement when we talk about shear strength and shear design. Okay, so remember that we're going to use VC. And let me write that up here so we can remember. VC equals 2 square root F prime C, again in PSI, B times D. That equals VC. Okay. Now this chart, anywhere from 0 to VC over 2 on your chart, you don't need stirrups. And again, I don't recommend this. I recommend that you put minimum stirrups everywhere. Next, anywhere from VC over 2 to VC plus 50 BD. Remember, if you put AV, minimum AV into the VS equation, it ended up being 50 times VD. So anywhere on your shear diagram from VC over 2 to VC plus 50 BD, you're going to use minimum stirrups. And these are the equations you're going to use. And the spacing has to be less than D over 2. Increasing on your shear diagram, anywhere from VC plus 50 BD to VC plus 4 square root F prime C BD, you're going to have strength stirrups, and you'll use these equations, and S is less than D over 2. Now, this is where I want to use the concept of we're measuring everything in terms of VC. Can you see that 4 square root F prime C is 2 VCs? Because 1 VC is 2 square root F prime C BD. So that's a total of 3 VC. Similarly, can you see 8 root is going to be 4 VCs for a total of 5 VC. So anywhere on your shear diagram, we get from VC to 50 plus 50 BD up to 3 VC, you're going to have S less than D over 2, and you're going to use those equations there. And anything from 3 VC to 5 VC, you're going to use the same equations, but the maximum spacing now decreases to d over 4. And finally, what if you're greater than 5 VC and outside the table, your beam is too small? You need more VC, increase the size of the beam. If you design your beam for flexure for a reasonable amount of steel, let's say halfway between rho min and rho max, that will make the size of your beam big enough where this won't happen. You won't be above 5 VC. Okay, one last thing about this table. What is this VS in these equations here? Remember, phi Vn has to be greater than Vu, or Vn has to be greater than Vu over phi. And remember that Vn is Vc plus Vs. That means that Vs is Vu over phi minus Vc. The amount of shear your stirrups need to cover is whatever the concrete can't cover. This right here, Vu over phi, is the required Vn. You subtract off the amount of shear you can get out of the concrete, and whatever's left over, you have to make up that difference in the stirrups with Vs. And that's how you use that. Just some comments on that table. When I keep saying shear diagram, I mean Vu over phi, okay? It comes from this, right? Phi Vn greater than Vu, so Vn has to be greater than Vu over phi. What you're gonna do, you're gonna have some kind of diagram. Okay. You're gonna have Vu, and then you're gonna divide that by phi, which is 0.75. Okay. And then it'll get bigger because you're dividing by a number smaller than 1. In fact, dividing by 0.75 is equivalent to multiplying by 4/3, the reciprocal of 0.75. And this is where you're gonna start chopping up your diagram to VC plus 50, BD, 3 VC, 5 VC. Hopefully you have to be less than 5 VC on there. And when you split up your shear diagram, then you come to this table and you design accordingly. Well, that means you need to be able to get a shear diagram, and we do have approximate shear diagrams just like we had approximate moment diagrams using ACI coefficients. That will be in the next lecture.